While the class of functions that we've been studying, second-order differential equations with constant coefficients, offers a narrow scope of differential equations, studying them is important because they serve as models of many important applications. Right now, we will study the motion of a mass on a spring, as its theory is applicable in many situations. We will consider a mass hanging vertically from a spring, stretching it downward. When this mass-spring system is in equilibrium, the mass has two forces acting on it. The weight of the mass coming from gravity, which is given by mass times gravity, and the opposite force due to the spring. We'll call this F sub s. Since it's in equilibrium, we know that F sub s is equal to the weight m times g. And the force F sub s can be found by Hooke's law, telling us that F sub s is proportional to the elongation distance L that the spring is stretched from equilibrium. F sub s equals negative k times L, where k is that proportionality constant. We call it the spring constant. And since the force is acting in the opposite direction that we pull the spring, it will have a negative proportionality constant. So we'll write this as negative k, where k is positive. Now, since the mass is in equilibrium, we know that the sum of these forces is zero. That is, the force of weight, mass times gravity, plus the force from the spring, negative k times L, is equal to zero. Or rewriting it, mass times gravity is equal to k times L. This gives us a way to find that proportionality constant k, because the elongation length L can be measured along with the mass or weight. So that leaves the only unknown constant as k. Since there's not much to study if we leave our mass spring in equilibrium, suppose that we stretch the mass from equilibrium by length u, and then set it in motion. The forces that we just discussed, F sub s equal to negative k times L plus u now, and the weight, W equals m times g, still are acting on the mass. But for a mass in motion, a damping force, F sub d, from friction and air resistance will now be acting on the mass as well. This force will be proportional to the velocity u prime. In particular, we'll write F sub d as negative gamma times u prime, where gamma is greater than or equal to 0 and called the damping coefficient. Again here, the force is acting in the opposite direction of velocity, so we want our proportionality constant to be negative. So we write it as negative gamma for a positive gamma. Or in the undamped case, we have gamma equals 0. So now the total forces acting on the mass are given by negative k times L plus u, plus the weight, m times g, plus the force from damping, negative gamma times u prime. And we can simplify the right-hand side by distributing negative k onto L plus u, and using that k times L is equal to m times g, so the right-hand side simplifies to negative k times u minus gamma times u prime. On the other side, we can rewrite force as mass times acceleration using Newton's second law. And since acceleration a is u double prime, we can write the left-hand side in terms of u as well. Mass times acceleration we can rewrite as mass times u double prime. And now, moving everything to one side, we'll have m times u double prime plus gamma times u prime plus k times u equals 0. A second-order differential equation with constant coefficients, as we've been studying.